And again, now you're moving materials and usually additional waste products from the blood back into the capillary, the blood, actually the peritubular capillaries, into the renal filtrate, in the renal tubule. So now you're going from blood back into renal tubule. Okay, so first you go from blood into the renal tubule, Bowman's capsule, glomerular filtration. Then in tubular reabsorption, you're going from the renal tubule back to the blood. Now in tubular secretion, you're going from blood back to the renal tubule. So this takes in additional waste products. Again, the selective process, the kidney here then can get rid of waste products that were not already in the renal filtrate. For example, when we metabolize drugs, we break them down. A lot of them are excreted into urine. As you know, they'll often do drug tests to see what you've been using, okay, what drugs you've been taking, okay. Prescription drugs are happy drugs, whatever. And often when you apply for a job, they want to do a urinalysis to test. Okay. You're also going to excrete substances that were previously reabsorbed by diffusion, waste products like urea and uric acid. Also, you're going to eliminate excess ions like potassium ions that were mostly previously reabsorbed. Okay. You're also going to get rid of amounts of waste products already in the renal filtrate, additional amounts like ammonia, ammonium ions, and creatinine. So basically it's getting rid of more waste products. Some that may have been reabsorbed or some that didn't get put into the renal filtrate in the first place. Okay, and also too, it aids in regulating pH in the blood by what ions are secreted. And that's going to vary depending on whether you want to bring the pH up or pH down. Because one of the things the kidney, we mentioned another thing the kidneys do is also not only get rid of waste products, but also adjust the pH. So for example, when the blood pH is too acidic, now the kidneys are going to, as you can see, more hydrogens are going to be secreted into the renal filtrate and pass out of the urine. More bicarbonate ions, which are base ions, and potassium ions are going to be reclaimed from it. The other extreme, when the blood pH is too alkaline or too basic, now more chloride ions are going to be reabsorbed, fewer bicarbonate ions are going to be reabsorbed and pass out of the urine. So by adjusting ion levels, the kidneys can also adjust pH, to regulate pH in the body fluids. And notice too that most tubular secretion occurs again in the proximal convoluted tubule, just like tubular reabsorption, but it also occurs in the loop of Henle, and also the distal convoluted tubule, and even the part of the collecting duct in the cortex, the cortical part of the collecting duct. Potassium ions occurs primarily in the distal part of the distal convoluted tubule, and also the cortical part of the collecting duct, that part of the collecting duct that runs the cortex, through the cortex and the middle. Okay? Any questions? Okay. All right, let's look now at regulation of urine concentration. But remember, the kidneys have to concentrate the urine. They've got to reclaim most of the water, which means most of the water has to be pulled out of the renal filtrate and not pass out of the body as urine. So they've got to concentrate that urine. And basically, this is accomplished by what's called a countercurrent mechanism. And this occurs in the medulla of the kidneys. It involves part of the nephron called the loop of Henle. Remember, that's the only part of the nephron that extends into the medulla. All the rest of the nephron, the renal corpuscle, proximal convolute tubule, distal convolute tubule, and even part of the loop of Henle is in the cortex. So what we're talking about here is the part of the loop of Henle that extends down in the medulla. And primarily the loop of Henle of what type of nephron? Remember we talked about two types, cortical and juxtamedullary. Juxtamedullary? Yes, the juxtamedullary. They're the ones that have the very long loop of Henle, most of which is in the medulla. So again, we're talking about movement from the renal filtrate in that tube, loop of Henle, into blood capillaries that surround it. And what are those blood capillaries called? In the medulla. Vasa recta. The vasa recta. Okay? So the kidneys basically keep the solute concentration of body fluids at a fairly constant level, as that of the blood plasma, and they do this by adjusting concentration and binding the urine. And again, the mechanism is called countercurrent mechanism. Okay? By the way, it also involves hormones. Now, the countercurrent mechanism basically is what enables the kidneys to vary that solute concentrated urine. And they do it by maintaining an osmotic gradient in the medulla through which the loop of Henle is flowing. And we got your descending limb coming down from the cortex into the medulla, then you have your ascending limb going from medulla back into cortex. Now this is called a countercurrent mechanism because the flow of the fluid, the renal filtrate, is in opposite directions. In the descending limb, it's going one direction, from cortex into medulla, and in the ascending limb, it's going from medulla back into cortex. So countercurrent. Now, it's, as I said, it's primarily loop of Henle in the juxtamedullary, the juxtaglomerular nephrons, okay? And in this case, the filtrate basically flows into the medulla. It creates an osmotic gradient, and thus we call the loop of Henle the countercurrent multiplier. This is basically what establishes this gradient. It's an osmotic gradient. This has to do basically with the ions in the medulla versus the iron concentration in the loop of Henle. Now notice that the loop of Henle, the descending limb, is permeable to water, which means water can readily flow across the walls of the descending limb of the loop of Henle into the medulla of the kidney. But the descending limb of the loop of Henle is impermeable to most solutes. So only the water is going to move out, not the solutes. But the solute concentration of interstitial fluid, that's the fluid outside the cells of the medulla, which surrounds the loop of Henle, is going to increase as that fluid in the loop of Henle is moving from cortex down to medulla along this descending limb. So what happens, of course, is since you've got more solutes outside the loop of Henle, what's it going to do? So hypertonic environment is going to pull water out of that descending limb into the interstitial fluid surrounding the loop of Henle. And of course, at the same time, it's increasing the solute concentration in the glomerular filtrate in the loop of Henle, because only the water is moving out, not the solutes, because that wall of the descending limb is impermeable to solutes. However, in the ascending limb of the loop of Henle, where it's going from medulla back into the cortex, you can see this is permeable to solutes, but impermeable to the water. So now the solutes can move, but not the water. So sodium and chloride ions are basically going to be reabsorbed from that filtrate in the ascending limb, and they're going to pass from the renal filtrate of the loop of Henle into the interstitial fluid in the medulla. What does this do? It creates more of a hypertonic environment. So as that fluid is coming down in the descending limb, it's exposed to this hypertonic environment, the interstitial fluid surrounding the loop of Henle, and it's pulling that water out passively by osmosis. And since you're pulling water out, if you had nothing, To counterbalance it, what would happen? Pretty soon, you're going to have so much water that it no longer becomes a hypertonic environment. But since you keep pointing out sodium potassium ions in the ascending limb, you just keep building up that hypertonic environment, or maintaining that hypertonic environment. So again, the movement of ions from the loop of Henle in the interstitial fluid then, by the medulla, creates this hypertonic environment. And again, that's what's going to draw the water out passively by osmosis. Remember, water is going to follow the solute. So water's coming down in the descending limb, which is permeable water, but not the solutes. Water's pulled out because that interstitial fluid surrounding the tube is what? Full of solutes. It's a hypertonic environment that pulls the water out. But then as it rounds the corner and goes up in the ascending limb, now the water can't come out, but solutes can. So the solutes are contributing to that hypertonic environment because you're pulling out especially sodium and chloride ions. Okay? So again, this is the countercurrent multiplier, the loop of Henle. Those longs loop of Henle that pass down into the medulla. Okay? Any questions on this? Now also notice that the distal part of the collecting ducts is permeable to urea. And urea, of course, is a solute as well. That's a waste product. And remember, the collecting ducts run from the cortex down to the medulla. And eventually they join with one another to form papillary ducts, which then drain the fluid, which is urine now, into a minor calyx, which drains each renal pyramid. Okay, so with the distal part of the collecting ducts being permeable to urea, what's going to happen? Well, urea diffuses out the collecting ducts in interstitial fluid. What does this do? Adds more solute, makes that even more hypertonic environment, more solute added. Not just sodium chloride ions, but now also urea is coming in from the collecting ducts. So again, you increase that high solute concentration, and again, that's what's pulling the water out of the descending limb of the loop of Henle, and the water again just moving by osmosis, passive process. Okay? Now there's another element in the equation, and that is the vasa recta. The vasa recta, remember, those are the capillaries that surround the loop of Henle in the medulla. And this is what maintains an osmotic gradient. And therefore it's called, the vasa recta is the countercurrent exchanger. The walls of the vasa recta, remember these are capillaries in the medulla, are permeable both to water and also to sodium and chloride ions. So when the blood flows through it, from cortex and medulla, it's going to lose water. Again, why? Because it's flowing through a hypertonic environment. Again, that's going to pull the water out by osmosis. Okay? But it can also pick up some of the sodium chloride. Because remember, it's permeable to both solutes and to water. When the blood flows then through the vasa recta from the medulla back into the cortex, it's going to gain water again, okay, and lose the sodium chloride. So it's basically maintaining the status quo. It's maintaining what was there. So the net effect is to do what? Gain water. So this is how water gets back into the blood. You're pulling water from that renal filtrate that was originally in the loop of Henle. Now it gets into the blood capillaries, the vasa recta, goes back to the blood, builds up the blood volume, can build up the blood pressure. So what you're doing is doing what? You're pulling more water out, leaving more solute in, you're concentrating the urine. Again, blood entering the vasa recta and leaving the medulla is a similar solute concentration. So this vasa recta basically is the maintaining that osmotic gradient in the medulla. This is from your textbook, which illustrates what's going on. This represents kind of a simplified view of the nephron. Okay, up here again, this is the renal corpuscle, which of course is in the cortex. This is cortex up here above the dotted line, and then below, we're down here in the medulla. Okay, this represents the proximal convoluted tubule. Again, simplified version. This is the loop of Henle. And specifically here, the descending limb of the loop of Henle, the ascending limb of the loop of Henle. This would be the distal convoluted tubule, and of course it would come out of the collecting duct. But you can see the descending limb of the loop of Henle is permeable to water, but not to solute. And since you got a high solute concentration out here in the interstitial fluid that surrounds the liquid family, you create a hypertonic environment, this is going to pull that water out by osmosis. And this, by the way, represents the milliosmoles, which is a measure of concentration of a solute. In this case, you can see what's happening is, since the water is pulling out, what's happening to solute concentration? It's increasing. So you can see the solute concentration increases, we go down here. Then as we go, the fluid now goes up into the ascending limb of the liquid family. Now it's reversed. Water can't come out, but solute can. So solute can come out, okay? Some it's actively moved out, some basically is passively moved out. But what this is doing is increasing the solute concentration in the interstitial fluid that surrounds the liquid family. So you maintain this hypertonic environment, which is going to pull the water out. Question?
No, is that able to have solute come out in the ascending loop because of the change in that fluid?
It comes out because the wall is permeable to the solutes, but not to the water. So now the water that's there is going to stay active. Unless it's going to be pulled up by some other magnetic hormone.
Which molecule is physically bigger though, H2O or the sodium?
Well,
I got no clue.
H2O, okay, what's the weight of
Yeah. Well,
sodium chloride, okay, would be about, of course, it's going to be ions, maybe about 58